You can do many things with a set of vectors, such as adding each vector in each set to the other one as many times as you like. You can add vector 1 to vector 2 6 times if you wanted, and this actually has a specific name. When you have a set of vectors where all vectors are an element of the vector space and you have at least one vector, you can add them in something called a linear combination, which is essentially just adding any vector you want in any multiple of each other. You can create a new vector with the vectors that you have, which could be v, it could be u, it could be t, it could be anything. Now, a specific type of linear combination is something called a spanning set, which is where you combine all linear combinations that are possible. And it is abbreviated to span of S, or however your set is abbreviated to. So every span is actually a subspace, and we're going to do a proof showing that. A subspace has three conditions. The first being that the zero vector must be an element of your set. The second being that your set is closed under addition. And lastly, the set must be closed under scalar multiplication. So how is a spanning set, or every spanning set, a subspace? Firstly, if we equate every constant to 0, we will create a zero vector. So 0 is a linear combination of the vectors in S. Therefore, 0 is an element of the span S. Now, to prove that every linear combination of a set is in fact a subspace, we need to prove the second law of a subspace, which is it must be closed under addition. So of course start off by saying that the vectors are an element of span S, then write down that there are scalars, ci and bi, it can be any letter you want, as long as you state that the subscript I is between 1 and whatever element k you want it to be. And then you need to write down your first two conditions, which you should denote with a 1 and a 2. The next step is to add your two equations and then rearrange to make the statement true. So as we can see, adding two scalars will give a scalar. So adding this, the second law of a subspace holds. Make sure to conclude. So u plus v are an element of span S, since our scalars are an element of real numbers for all I. Now, to prove that a spanning set is closed under scalar addition, we need to state that we're dealing with a vector which is part of our spanning set, and that we're dealing with a scalar which is an element of all real numbers, but it doesn't go below 1. So we're dealing with this could be any linear combination a part of our set T. So now let's check for how this reacts when we multiply it by a scalar. So as you can see, everything just multiplies by a scalar. And rearranging this will just land us with a different linear combination. So, given we have just proved that BV is an element of span S, since we have proven that multiplying a vector by a scalar still remains an element of all real numbers for all I. So we've proven all three subspace conditions. So what's so great about this? Well, with this concept, we can easily find any subspace. So here's your summary. Feel free to pause the video and have a look, but I hope that was helpful.